spotlights and 1 oral. And we're going to start with 4 spotlights, then switch on oral, and then another 5 spotlights. And we're starting with deep network for the integrated 3D sensing of multiple people in natural images, presented by Andrei Zanfir.
Hello, everyone. My name is Andrei Zanfir, and I'll be presenting the paper entitled Deep Network for the Integrated 3D Sensing of Multiple People in Natural Images. This is joint work with my wonderful colleagues, Elisabeta Marinoiu, Mihai Zanfir, Alin Ionuț Pupa, and Cristian Smichișescu at Lund University, IMAR, and Google Research. Our goal is to build a feed-forward system that is able to localize multiple people and estimate their 3D pose and shape in monocular images. This is a challenging problem due to the presence of multiple people, occlusion, and because of depth ambiguities in any single monocular image. It is also difficult to formulate a single cost function and an integrated learning process. In order to achieve this, we present MubiNet, a feed-forward multitask network which supports simultaneous multiple people localization as well as 3D pose and shape estimation. Multitask losses constrain the output of a change of processing on top of an input image I. One of the key difficulties is to integrate the discrete and continuous nature of the optimization process during inference and learning. Identifying a variable number of people is inherently a discrete constraint grouping problem, whereas predicting their pose and shape is a continuous one. Moreover, we want to be able to work within an integrating volume representation and directly reason in a combined 3D space, as opposed to break down the problem into 2D person detection and 3D reconstruction, which can be suboptimal and thus error-prone. The deep volume encoding module regresses volume containing 2D and 3D pose information. To encode the 3D skeletons of multiple people, we associate a slice in the volume to each body joint component and store the skull skeleton configuration at the 2D spatial layout of each person. Our representation is motivated by the need to predict a variable number of person or outputs, redundancy for occlusion handling, thus we encode the whole in each part, and local spatial support, but non-local information coverage for prediction. To regress such a 2D, 3D volume, we adopt a multi-stage approach. Within this deep encoding, heat maps of body joint detectors emerge with their type, let's say knee or ankle, assignment for a particular person. In order to support the localization of multiple people, we group the estimated joints into skeleton predictions by using 3D information. First, we need a function to assess the quality of different limb hypotheses, where a limb links any 2 body joints that can be connected in a human kinematic chain. In order to learn the scoring function C, we introduce an additional natural layer called limb scoring. We sample deep volume features along the putative limbs and regress the corresponding binary connection scores. We pose the problem of identifying the skeletons of multiple people as a binary integer program where we encode the following properties as inequality constraints. The endpoints of selected limbs cannot have multiple assignments, and they are subject to kinematic ordering constraints. In the bottom left plot, we show the distribution of initial learned score C in blue and the distribution of the solution obtained after solving the binary integer program in yellow. Notice that the 2 distributions are close, showing a well-tuned function. Because only kinematic feasible constraints are generated, the optimization is efficient as running times are in milliseconds. This also scales favorably in the number of putative limbs as shown in the bottom right plot. At the end of these stages, we have a partitioning of the volume encoding into the structures associated to different people. An immediate way of decoding the estimated 3D volume into 3D body joints estimates for all the person in the image is to average 3D skeleton prediction over the associated volume support. We explore this as well as more sophisticated detection mechanism in the paper. In order to infer the 3D pose and shape of each person given a 3D set of body joints, we employ a volumetric human model with parameters theta and beta respectively. We formulate pose and shape reconstruction as auto-encoding. More details are in the paper. We test our network on single and multi-person dataset as well as qualitatively on molecular images captured in the wild. On the large human 36.m dataset, we obtain state-of-the-art results. For evaluating the reconstruction of multiple people, we use the CMU panoptic dataset where we improve over the prior base result. If we further fine-tune the network, the error is half. We test our method on challenging non-laboratory molecular image setups with partial views, occlusions, skew camera angles, and obtain plausible body shape configuration. Thank you much for your time, and I wait you for the poster.
So next one up is Delta encoder and effective sample synthesis method for few-shot object recognition, presented by Eli Schwartz.
Hi, bonjour. I'm Eli Schwartz from IBM and Tel Aviv University. We present Delta encoder, a generative model that enables few-shot object recognition. Given as little as one example per novel unseen class, we generate more samples that are then used to train a classifier. This is a joint work of IBM, Tel Aviv University, and the Technion. So here we see our classification results giving only a single example of golden retriever and a single example of wild African dog, both marked in blue. In pink are the correctly classified golden retrievers, and in yellow are the correctly classified wild African dogs. Notice that in terms of proximity in the feature space, some of the golden retrievers are closer to the seed wild African dog than to the seed golden retrievers. Nevertheless, our generated samples were able to bridge this gap. So let's see how it works under the hood. Our model is a variant of an autoencoder operating in some feature space, meaning inputs and outputs are feature vectors. The encoder accepts a pair of images belonging to the same training category. Let's call them reference and target. The reference, in this, the encoder learns to encode the delta or the transformation between the pair of images. In this example, the reference is a boy with a natural expression, and the target is a smiling boy. The delta would be the deformation, the natural to smile deformation. The decoder learns to recover the target based on the reference and the delta. Back to our example, the decoder will apply the neutral to smile deformation to the reference image to recover the smiling boy. Let's see how we generate new synthetic samples for novel unseen classes. First of all, we sample a random delta by sampling a random pairs of images from the same training category. Then the decoder is used to combine the sampled delta with the few provided examples from a novel category to generate synthetic samples that are then used to train a simple linear classifier. In our example, we observe a neutral expression novel girl category, and by applying to it the neutral to smile sample delta, we generate a smiling girl we haven't seen before, and so enriching our training set for the novel category. We tested our method on four standard few-shot benchmarks, namely Mini ImageNet, CIFAR100, Caltech 256, and Caltech BIRDS. We observe an average improvement over previous state-of-the-art of 3.6 points in accuracy. On the top right, you can see the red crosses representing the single examples for novel categories, and the clouds around them are our generated samples. If we zoom in on one category, we can visualize the generated samples by looking for their nearest neighbors in the feature space, and you can see that our generated samples cover a wide range of real samples. We observe in our experiments that accuracy improves as we generate more samples, suggesting we keep generating meaningful information. Interestingly, generating many synthetic samples surpass the results of just adding few more real samples. Thank you for your attention, and we'll be happy to answer more questions and discuss more at the poster session. We are poster number 25.
Thanks, the speaker. So next we have text-adaptive generative adversarial networks manipulating images with natural language, presented by Seung-Hwin Nam.
Good morning, I'm Seung-Hwin Nam from Yonsei University. Today I'm going to introduce our paper, Text-Adaptive Generative Adversarial Networks Manipulating Images with Natural Language. In this paper, we are interested in the problem of manipulating images with natural language. For instance, a user who has a picture of a bird may ask a computer program to change the appearance of the bird by describing a target appearance in text. Then the computer program automatically produces a new image by changing the original image according to the text. In other words, our goal is to modify visual attributes of an object, where the visual attributes are characterized by the color and the texture of an object. Our work is closely related to GAN-based text-to-image synthesis methods. Conventionally, sentence-level conditional GANs have been used for the synthesis. However, when applied to our task, this approach often fails to generate plausible results. For example, text-irrelevant contents like background are not preserved, as you can see in this figure. In this paper, we propose the text-adaptive generative adversarial network to overcome this limitation. Our key idea is to split a single sentence-level discriminator into a number of word-level local discriminators so that they provide fine-grained training signals to the generator. This figure shows the overview of our method. Basically, our generator takes an input image and its target text, then change the original image according to the text to fool the discriminator. We constrain our generator to reconstruct the original image when its ground truth text is given to preserve the original contents. Our discriminator consists of an unconditional and text-adaptive discriminators. The key of our method is the text-adaptive discriminator that makes the generated image match the text. Specifically, our text-adaptive discriminator produces a number of word-level discriminators on the fly according to the input text. Each local discriminator is specialized in detecting a specific type of visual attribute. We additionally compute word-level attention to reduce the impact of less important words to the final score. We also consider multi-scale image features to make the local discriminators detect both coarse and fine-grained visual attributes. Finally, we aggregate all the local discriminator scores with the attentions in a multiplicative manner to compute the final score. We evaluate our method on CUV dataset. As can be seen, our method effectively changes a variety of images according to diverse texts, while preserving text-irrelevant contents. Our method is also effective on Oxford dataset. Especially, our method is able to generate visual attributes on diverse input images, regardless of pose, shape, and background. Compared with existing methods, our method outperforms them in terms of visual quality and better preserves text-irrelevant contents. If you are interested in more information about our paper, please visit our poster. Thank you.
All right, so next we have neighborhood consensus networks presented by Ignacio Rocco.
Hello, I'm Ignacio Rocco, and I'm going to present the paper Neighborhood Consensus Networks. Some technical issue.
Control L. And then
It was stuck. Yeah, thanks. So in this work, we tackle the problem of image correspondence. We're given two images. We would like to obtain point-wide matches between the corresponding image parts, such as in this example. In particular, we consider challenging situations, such as matching the same object across day and night illumination, or matching the same scene changing over time, or matching indoor scenes with repetitive structures, or matching different objects from the same class with large intra-class variation. Finding visual correspondences is important for several applications, including vision-based localization, 3D reconstruction, or transferring localized annotations to new images. Traditionally, the problem of finding image correspondence has been tackled by first extracting sparsely located image features using methods such as SIFT, then obtaining tentative matches between these features, and finally filtering these matches using global or semi-local geometric constraints to remove the incorrect correspondences. In this work, we focus on the semi-local geometric filtering method called neighborhood consensus. In neighborhood consensus, the quality of a match is assessed by counting the number of spatially consistent neighboring matches. For example, in this first match with spatially consistent neighboring matches, it's deemed as correct, while the second match, where the neighboring matches are not spatially consistent, is deemed as incorrect. In this work, we build on the classic three-stage feature extraction, matching, and filtering pipeline, but using trainable components. In particular, we propose a novel neighborhood consensus network for geometric match filtering. I will now describe our approach in more detail. First, we employ a fully convolutional neural network to obtain dense feature maps for each of the input images. Then, for every pair of features, we compute a similarity score and store it in a four-dimensional tensor. Note that this tensor contains all possible pairwise matches, many of which are incorrect. Therefore, we propose a neighborhood consensus network that takes the 4D matching tensor as input, filters out the incorrect matches, and produces a filtered 4D matching tensor as output. This is achieved using a sequence of 4D convolutional layers. Note that the 4D filters from the first layer span a local 2D neighborhood in each of the images and capture geometric patterns of correspondence that are in consensus between the two images. Then the subsequent layers capture even more complex geometric patterns of correspondence in the 4D space of all possible matches. The output is an improved, geometrically consistent set of matches without the need of a global geometric model. In order to train the model, we use a weakly supervised approach where only supervision at the image level is required, such as positive pairs, where images depict the same scene or objects, or negative pairs, where images depict different scenes or different objects. The proposed training objective then maximizes the overall matching score of positive pairs, while minimizes the matching score of negative pairs. We first evaluate the proposed method on the problem of category-level matching using the PF Pascal dataset. Here, given annotated object parts from the first image, the task is to find their corresponding locations in the second image. The neighborhood consensus network successfully transferred the annotated part locations to the second image. These transferred part locations are close to the annotations provided by humans. Note that the method is able to obtain correct correspondences despite large changes in appearance due to the intra-class variation. We also evaluate our performance on a very different problem of accurate camera localization in indoor environments, which has application in robot navigation and augmented reality. Here, given a query image and a known 3D model of a building, the task is to recover the exact position of the camera inside the building. This is done by first using an image retrieval method such as NetLab to recover an RGBD database image with a similar viewpoint, and then computing pixel-wise correspondences between the query and the database image. Finally, the perspective endpoint algorithm is used to recover the camera pose from the correspondences. Here we show an example using the state-of-the-art in-lock approach that matches every key point independently. The repetitive window structures have caused a mismatch, which resulted in a large pose error. Our method, on the contrary, is able to detect coherent matching patterns and filter out the incorrect matches due to the repetitive structures in this example, which results in a much smaller camera pose error, as also shown in this 3D view depicting the two recovered camera poses, demonstrating the advantage of our method. Overall, our method outperforms the state-of-the-art in-lock method for camera localization in this challenging benchmark. Thank you for your attention. For more details, please check out our website or come to our poster upstairs.
We're switching to the oral now. So this work is visual memory for robust path planning, path following, and it's by Ashish Kumara, Saurabh Gupta, David Poi, Sergey Levin, and Jitendra Malik. And Ashish is going to give a talk.
Good morning, everyone. I'd like to begin this talk by talking about navigation strategies in animals. Mice are well known to develop efficient navigation strategies for foraging and navigation. And this is also commonly seen in birds and mammals which develop spatial maps of their environment. In particular, when a mice is dropped in an unknown new environment, it starts off by just following the odor plumes in the environment, but then switches to a systematic exploration of the environment as it gathers more spatial knowledge. Another characteristic of navigation is the use of visual landmarks, even by very simple animals such as insects, which have far fewer neurons. In a 1951 experiment by Nico Tinbergen, he found that wasps use the pebbles around their nest as a cue to locate their nest. When the nest was moved outside the pebble cluster, the wasp still flew to the center of the pebbles, implying that it was a visual landmark being used by the wasps. In fact, we use visual landmarks almost every day to navigate. So although on the first day of the conference, you may have used maps to get to the conference venue, but from the second day onwards, when you enter the conference building, you remember to go straight past the resto bar and the food joint, and then you take a left towards the elevator to get to the conference venue. Now, at first glance, this may seem like a trivial ability that we have. But if you look closely, this is a remarkable ability wherein we don't even know how much we have precisely walked. And yet, we manage to get it right every single time, despite drastic changes in appearance and viewpoints. Now, the current approaches to solve the problem construct a full 3D model of the environment and then plan on top of it. Surely, this is an overkill. These maps are doing too much by building very accurate models and yet too little at the same time by being hostage to these models, which might become obsolete very quickly. Do we really need to reconstruct this trash can just to go past it? In fact, even if we do manage to reconstruct these humans very accurately in this model, this 3D model of the environment will become obsolete the moment they leave the scene. So these methods are clearly doing too much and too little at the same time. So how do we approach the problem? One way to approach the problem is to use end-to-end learning, where we hope that the right semantics will be learned automatically in a data-driven way. Now, if we take a closer look at the problem of navigation, we see that the problem can be broken down into path discovery and path following. So path discovery refers to finding a path from A to B, which can happen via verbal directions, following someone who already knows the path, by planning on a 2D map, exploring, etc. Most of the end-to-end learning work has focused on this paradigm. Now, once we have figured out a path from A to B, we would like to robustly follow it, even under environmental changes. And this is what today's talk will focus on. More formally, given a single demonstration of the path, which we call the reference trajectory, this translates to a sequence of observations and a sequence of actions. And we would like to robustly follow the path under a noisy actuation model of the robot and a potentially changing environment. Now, to understand the challenges of the seemingly simple task, let us look at what each of these mean. For the noisy actuation model, we imperfectly execute the robot actions of rotating and moving forward under a truncated Gaussian noise model. We also ask the agent to retrace the path under a changed environment in comparison to from where the reference images were taken. Now, to look at their implications, let us look at some top views of these cases. So for the noisy actuation model, I've shown the reference trajectory in red, and we roll out the reference actions multiple times from the same starting position, which is shown in blue. And we observe that under the noise model, out of the 20 rollouts, only 3 of them roughly end up going towards the goal. On the right, I've shown the free space in white and the obstacles in black. The red reference trajectory, which was given in the original environment, may no longer be feasible due to new obstacles on its way. Now, these obstacles are shown in gray here. To understand, so how do we approach the problem? We start by operationalizing the idea of visual memory as seen in intelligent agents. So given a path, a trajectory, a reference trajectory, we generate a path abstraction, and then we use this abstraction to robustly follow the path. More concretely, given a sequence of image action pairs in the reference trajectory, we generate a path abstraction. We maintain a pointer which starts at the beginning of the path, and we then use this pointer to generate a feature vector, which is a weighted combination of all the path features that we have. We then combine this weighted combination with the current observation that we have, and we pass it through a deep neural network to generate an action prediction. This network also predicts an update to the pointer. In the next time step, we again use this weighted combination of path features centered at the pointer to generate a path feature, and the current observation to generate the next action prediction, and then again update the pointer. And to allow the agent to maintain temporal memory during its traversal, we implement the action and pointer prediction network as a recurrent neural network. To train our model, we start off with the path abstraction and unroll it in time to get a sequence of action predictions, and we then compare it to the ground truth actions using cross-entropy loss. An important thing to note here about our model is that we maintain a localization pointer for our method, but we never explicitly supervise it. The hope is that by training for the end task, the localization pointer will accurately localize only when necessary for the task. We evaluate our methods in 2 simulation environments. The first is based off of a real-world scans of MP3D buildings and Stanford buildings. And the second simulation is SunCG, which consists of synthetic indoor environments where the spaces and the furnitures have been manually designed. For the baselines, we compare with the following. So we compare with the open loop baseline, where we simply replay the reference actions. Note that in expectation, the open loop will get to the final goal under no obstacles. We also compare to 2D visual servoing, where we start off with the current observation and the first observation of the reference as the target image. We simulate the 3 actions and compute the spatial distance of the matched features, and we then execute the one with the least spatial distance. We continue doing this until we get to the first reference trajectory, at which point we move to the next reference trajectory and continue. We also compare to 3D reconstruction plus localization, where we start off with a traversal of the environment, which is the reference trajectory. We construct a 3D point cloud of the environment, and when given a new image, we try to localize this image in the environment by matching it to the point cloud that we have. We then use this localization to plan on an estimated free space. Note that this method does remarkably well when there are no changes in the environment. However, under environmental changes, its performance drops drastically, which is due to the fact that SIFT localization fails when the observation that we are looking at is different from the point cloud that we constructed from. And lastly, to understand the importance of visual memory, we also compare to a baseline without visual memory. So here, we simply drop the reference images that we have. Now let us look at some results. So we evaluate all the methods using success percentage, which measures the percentage of times the agent gets to within 10% of the initial goal distance. So we see that 3D reconstruction plus localization does really well, almost approaching the accuracy of our method. To get a sense of what is happening, let us look at some visualizations in first-person view. So this is the reference trajectory which is given to all methods. It is shown as red in top view on the right. Note that the top view is not available to any of the methods, and it is just for visualization. This is our method, which starts off, ends up following a trajectory slightly different due to actuation noise, but does end up eventually getting to the final goal around the hall. Now this is 3D reconstruction plus localization, which does reasonably well until it starts facing a completely blank wall, at which point it fails to localize. To understand what is going on with the pointer that we introduced, we also look at the pointer visualization next to the actual location of the agent. So the blue line here shows the actual location of the agent, and the overlaid red plot shows where the pointer thinks the agent is. So as we can see, that the So the pointer only loosely tracks the agent and it's not accurate. It's accurate only when is needed by the model. We also evaluate the methods under environmental changes, where we show the reference trajectory in red here. And then we want the agent to follow this reference trajectory under a changed environment where the new obstacles are overlaid in gray. So note that along with changing the visual look of the environment due to new objects, the new obstacle may also render the existing path infeasible. So an example of a successful trajectory would be something like this, which goes around the obstacle and to the goal. When we look at the results in the changing environment, we see that 3D reconstruction plus localization falls down very steeply to 33, whereas our method maintains a reasonable performance. To look at some first-person visualizations, here is the reference trajectory where we see only one sofa and a single table in the next room. And when the agent actually follows it, we see that there are a lot more obstacles in the environment, and yet the agent goes around them to get to the final goal. We also evaluate all the methods under different amounts of changing environment. So here on the x-axis, we plot the number of percentage of obstacles in the environment. So the reference trajectory is drawn when there are 50% obstacles in the environment. And we drop the agent in an environment where there can be anywhere from 10 to 90% objects. So note that when the number of objects are lesser in the environment, the task might be much easier to solve. But despite that, we can see that the green curve, which is 3D reconstruction plus localization, ends up taking a hit in performance, both when there are more obstacles and less obstacles. And this is similar for most of the methods, except for open loop, which maintains its performance when there are less obstacles, because it simply replays the actions. Our method, on the other hand, maintains a reasonable performance throughout the entire trajectory of the x-axis. So in conclusion, we have proposed a method for path following based on visual memories, which can handle actuation noise and changing environment. Thank you.
Any questions? Please come to the microphones. Okay, I'll ask the first question. So you were motivating by people looking at semantic features like cafes and restaurants. Do you have a sense of what your network is learning for the visual features?
So So that's a good question. So the problem with learning features is that it is slightly hard to visualize what exactly it is learning, but to get a sense of what we do end up learning, we do visualize the pointer localization, which basically tells you what part of the reference trajectory the agent is picking up cues from. And that is what we showed here. So in the visualization that I showed where the localization pointer was trying to track the actual agent, we see that it is roughly around the agent. So the idea is that it just tries to look locally what to do to finally get to the task, but not exactly localize every single time.
Any other question? So I have one more maybe. Do you think you would benefit by having a floor plan or a map?
So for planning, it would, but like I mentioned, for the task of path following, fundamentally, it feels like it should be able to do without knowing the floor plan, because we do give a plan to the agent, which is simply by using the reference trajectory. So for the task of path following, that is a skill which is agnostic to the specific environment, and given that we know how to go from here to there, what we would like to evaluate in principle is without a floor plan, how well can we do, because biological agents do it almost perfectly every single time.
More questions? Okay, let's thank the speaker. So we have 5 more spotlights, and the first one is recurrent transformer networks for semantic correspondence, which is going to be presented by Sang-Yong Kim.
Hello everyone, my name is Sang-Yong Kim from Yonsei University. Today I'm going to present the paper Recurrent Transformation Network for Semantic Correspondence. This is joint work with Microsoft Research and Ewha Women's University. Semantic correspondence problem is to estimate the dense correspondences between semantically similar images, that is, the different instances within the same object or scene categories. Unlike the conventional correspondence problem, such as the depth or optical flow estimation, semantic correspondence poses additional challenges from photometric and geometric variation and lack of supervision. Photometric deformation derived from the intra-class appearance variation or attribute variation. Geometric variation derived from the different viewpoint or the non-linear shape deformation. Furthermore, annotating the ground truth correspondence field between semantically similar image is labor intensive and degraded by subjective. To solve this problem, the objective of this paper is to estimate the locally varying affine transformation field between semantically similar image. To solve this problem, a number of methods have been proposed, and they can be generally classified into 2 categories. The first one is method for geometric invariance in the feature extraction step. It can estimate the geometric field without using the ground truth geometric field. It is based on the formally special transform network. However, it still needs the ground truth flow field, and they estimate the geometric field by using the source or target image independently. The second method is the method for geometric invariance in the regularization step. It employs the additional geometric matching network to estimate the geometric field from source and target image. However, it can estimate the only globally varying special field, and they estimate the fixed and untransformed version of the feature. To solve this problem, we propose a recurrent transformation network. With the advantage of the STM-based method and geometric matching method. The key idea with this method is recurrently estimate the geometric transformation residual using the geometry aligned feature activation. Okay, let's see the details. In the feature extraction step, we extract the feature from source and target image by using the Siamese convolution network. In the second step, we construct the constraint correlation volume from current point I in the source image and the nearby pixel J in the target image. Unlike the conventional method, we use the constraint correlation volume to provide the robustness and computation efficiency. Finally, we estimate the locally varying transformation field by using the encoder and decoder network. By formulating the feature extraction network and the geometric matching network in the iterative manner, we can estimate the transformation field more accurately, progressively. To run our network in a weakly supervised manner without using the ground truth correspondence field, we proposed a novel loss function based on the intuitions that the matching square between source and target image at the same point should be maximized, while keeping the scores of other candidate low. Here we can see the experimental result. For source and target image, source images are warped to the target image by using the estimated dense correspondence field. As you can see here, our RTNs can provide more reliable dense correspondence field compared to the conventional method. In another benchmark, such as the PF Pascal benchmark, our method can estimate the highly reliable correspondence field comparing to the other method. In another examples, we can estimate the highly content-aware result comparing to the other method. To conclude this paper, we present the RTNs to learn and infer the locally varying geometric field for semantic correspondence. The key idea of this paper is to utilize and iteratively define the transformation and convolution activation field via matching between the image pairs. A technique is also presented for weakly supervised training of the RTNs. Thank you for listening. For more details and experimental results, please come to our poster. Thank you.
Hi. The next one, we have sequential attending for repeat generative modeling of moving objects. It's going to be presented by Adam Kosiorek.
Duplicate? Huh? Duplicate the display. Maybe try it directly. You have HDMI here.
Okay. Hi everyone. My name is Adam Koszorek, and I'm going to tell you how to use a generative model for unsupervised object detection and tracking. If you would like to find out more about the project, please visit us at the poster number 24. Let's start by talking about attending fair repeat, or AIR for short. AIR is a type of a generative model. It's a variational autoencoder which is able to decompose an image into objects. It does so by explaining every object by a separate latent variable, which can be then decoded back to the original image. Having separate latent variables for every object can be important from the point of view of reinforcement learning, where we might want to learn to do object manipulation, and also improves model interpretability, since it gives us a ready insight into what the model cares about and what data it uses to reconstruct the object. So in AIR, objects are explained by latent variables of different types. We have what, which tells us about the appearance of the object, where, which is the scale and the location, and the Bernoulli presence variable, which tells us whether the object even exists. So AIR is great in the sense that it allows us to do unsupervised object detection and tracking. However, if applied to image sequences or a video, it can work on separate frames independently, which means that there is no easy way to tie detections together. Moreover, it does not use temporal information, which can, where by using temporal information, we can stabilize the training of the model and learn richer generative models. For this reason, we extend AIR to sequential attending fair repeat, or SQUARE for short. Like in AIR, it models objects with separate latent variables, but here objects can appear and disappear in every frame. So SQUARE can model sequences of moving objects like this one, And any variational encoder could reconstruct this sequence even by working on every frame independently. However, with Square, we have one latent variable per object, we know their location, and unlike R, Square maintains identity of the objects, which means that we can do unsupervised object detection and tracking without any human supervision. Once the model is trained, because it's a generative model, we can sample from the model to check what the model learned about the data. So here we see that the object appearance does not change between frames as in the training set, and also the motion is consistent with motion seen in the training set. Once trained, we can perform conditional generation by conditioning the model on the first few frames of a sequence and predict the next ones by sampling from the prior. Here, the predictions differs from the ground truth, and this is because we use the noisy motion for the moving digits in the training set. Since Square is a stochastic model, for every conditioning sequence we can imagine different rollouts. Here we have 5 different predictions which start differing considerably from each other, which again reflects the uncertainty that the model is able to capture. We can compare Square and R directly in terms of reconstructing objects from partial observations. And here you can see that Square is able to reconstruct objects even if it misses a significant part of it, like the 9 on the left-hand side and 4 where it misses the stem, while R cannot recover identity of the object. Square is also much better at disentangling heavily overlapping objects, where here, even if digits overlap almost completely, it can recover them. R, on the other hand, treats overlapping objects as just a single object and misses the remaining object. We have also applied Square to real-world data, where we took videos from static CCTV cameras and we pre-processed them by removing backgrounds and inverting colors. As a result, Square learns to detect and track pedestrians without human supervision. Here, Square is trained on sequences of only 5 frames, but like in the MNIST experiment, we can condition it on the initial frames and try to predict the remaining sequence by sampling from the prior. On this slide, each row corresponds to different predictions, and we see that they start differing from each other, which again says that the model can capture uncertainty. Code for this project is available online, and if you would like to learn more about the project, please visit us at the poster number 24. Thank you.
So next one up is sanity checks for saliency maps, and it's going to be presented by Bing Kim.
Thank you. All right, I'm Bing Kim. I work at Google Brain. The main star of this paper is Julius, who unfortunately cannot make it to the conference. This work is about investigating a family of interpretability methods. Interpretability is about helping people understand the reasons behind predictions so that they can use machine learning more responsibly. This work is particularly about post-training interpretability methods. What does that mean? It just means that you have a model fixed, you train them, and your goal is to find the evidence of prediction. Let me be a little more concrete. You have a neural network that takes a picture and predicts what's in the picture. So in this case, given this model, your goal is still to find the evidence of prediction. In other words, why was this a junco bird? One of the most popular ways to answer this question is a technique called saliency maps. The promise of this technique is that it can identify important set of pixels that are evidence of prediction. In other words, these are the pixels why this picture was junco bird. Now, if these pixels are really the evidence of prediction, then when the prediction changes to something else, like the tree that this bird is sitting on, then the explanation should also change to reflect that prediction. In other words, not in other words, next. You can think about an extreme case where if the prediction is a complete garbage, a random prediction, then the explanation should really change. So we created such an extreme case. What we did is we took a beautifully trained Inception V3, got a lot of saliency maps for lots of pictures. And then we took the same network, copied it, and then we started randomizing, starting from the logic layer all the way down to the input layer. So remember, this network is now making garbage predictions. And because prediction and model changed in a dramatic way, you would think that explanation should also change. But it doesn't. Now, you may argue that, well, these two pictures look technically different. But remember, the final consumer of interpretability methods are humans. And as a human, I don't know if I will draw dramatically different conclusions based on these two pictures. The belly of the bird seems to be important. The cheeks of the bird seems to be important in both pictures. So is this really the evidence of prediction? This result makes me doubt. Here are full results, starting from the logic layer all the way down to the input layer. The last column is completely randomized network. As you can see, some methods visually don't change at all, even in complete randomization. Interestingly, the vanilla gradient, the top row, which a lot of these methods are based on, seems to be the best bet. We did another test. This time, we trained a network with completely random labels. So network is happy to overfit the random labels without really learning what it means to be digit 0. But the explanation still delivers similar message to the one that did learn what 0 means. Identifying the similar number of pixels, set of pixels, were important. Again, interestingly, the vanilla gradient seems to be the best bet. So what does this mean to us? Well, I think it says something pretty fundamental about how we evaluate interpretability methods. These methods were thought to work because when we give it to humans, it made sense to them. Classic confirmation bias. I think a better way to evaluate interpretability method is to have a couple of sanity checks. For example, you can craft an experiment where you know the ground truth and show that your method can match that ground truth. And this is kind of work that at the end of the day, you have more questions than answers. Some of these methods show that the explanation help humans do better in tasks. More studies needed to find out what these maps are showing and why they were helpful. Thank you.
All right, so next we have a probabilistic unit for segmentation of ambiguous images. It's going to be presented by Simon Cole.
Hi there. I'd like to walk you through our paper, a probabilistic unit for segmentation of ambiguous images. This will be poster number 127 just after this, and it will also be featured in the medical imaging workshop on Saturday. Images are often ambiguous, and this is particularly true for medical images. On the left here, you see lung abnormalities in CT scans, and to the right thereof, you see the annotations given by 4 independent expert graders. Evidently, they vary significantly. And what this work seeks out to do is to model distributions over segmentations given images. On the right here, you see a sneak peek of samples of our model. Semantic segmentation is usually approached in a deterministic fashion. That is, one assumes a one-to-one mapping between images and segmentations. A very successful model for semantic segmentation is the so-called unit. Now, our work proposes a probabilistic version thereof. We employ a prior network that is conditioned on the image and predicts a parameterization of a distribution over a low-dimensional latent space. Samples thereof are spatially replicated and then concatenated with feature map activations of the unit, further processed so as to decode sample by sample, and this results in a consistent segmentation hypothesis given the image at hand. Now, training proceeds with a cross-entropy loss, as is usual in semantic segmentation, but this is not sufficient by itself to learn a distribution over the latent space. In order to do this, we need an extra component during training, which is the so-called posterior net that, on top of being conditioned on the image, also is fed the segmentation itself. The prior and the posterior distribution are then tied together, pulled towards each other by means of a Kohlberg-Leiber divergence. And together these components form the well-known elbow objective. So this is really a combination of a segmentation model with a conditional variational autoencoder. The central component of this work is the latent space. So conditioned in the image here, we predict a distribution. In this case, it's a two-dimensional latent space, and this allows for a neat analysis of the semantic structure of this space. Here you can see, for this case, that the model chose the x dimension to embed size variations, versus the y dimension seems to encode more intricate shape variations. The distribution here is hinted upon by means of the yellow circles that stand for standard deviations of the Gaussian. And by means of the posterior distribution, we can also project the graders into this space. This is hinted upon by the green numbers here. And under our model, you can see that segmentation number 3 is deemed the most likely versus, for example, segmentation 0 is already 2 standard deviations away from what seems the best segmentation under our model. Quantitatively, we evaluate this on a long CT scan data set called LIDC. We compare the distributions induced by our model against the ground truth by means of looking at the different samples. And the evaluation metric chosen is the so-called energy distance, which is also known as the mean maximum discrepancy. We sample between 1 to 16 times, and the markers shown here denote the mean performance of the individual baselines. In green is shown our model, and when we sample more than once, you can see that our model is significantly better than the others in distribution space. Recall that semantic segmentation is usually approached deterministically, so the orange bar here shows how you would perform if you were to model this deterministically. So there's quite a gap if you evaluate in distribution space. In order for us to evaluate this quantitatively as for how well the models are calibrated, we use the Cityscape's street scene segmentation task and introduce artificial stochasticity. That is, we flip 5 classes to newly introduced classes, resulting in 2 to the 5, so 32 different modes. And we use different fixed frequencies for all of those modes so that we can now start to evaluate. On the very right here, you see samples of our model, and I want to point out that they're consistent, which is nice because they're all individually plausible, and this is in contrast, to other previous work that models uncertainties in semantic segmentation on the pixel level. Now, comparing the baselines calibration on this data set, we can look at the frequencies of the modes that our models comes up with versus the expected frequencies in these log P plots. On the blue diagonal would be optimality, and you can see the other models basically don't pick up on all models or are miscalibrated. On the right is our model in green, and you can see that it is actually very nicely calibrated. So to summarize, we propose a model that is able to learn conditional probabilities over segmentations. We're able to sample valid and consistent segmentations. This code is on GitHub. I'm told to stop here. Please come by at our poster. It's number 127. Looking forward to seeing you there. Thank you.
Oops. What's that? Oops. All right. And the last spotlight of this session, virtual class enhanced discriminative embedding learning, it's going to be presented by Bing-Hugh Chen.
Hello, everyone. Hello, everyone. This is Binghui. I'm going to present our paper, Virtual Class Enhanced Discriminative Embedding Learning. In most deep model architectures, SOMAX classifier is usually placed as a top layer. Due to the property of inner product between feature X and classifier parameter W, the SOMAX classifier mainly serves as an angular linear classifier. And when training with SOMAX classifier, the feature region of each class will be aligned by the class spot vector W. Our paper comes from the fact that for SOMAX classifier and d-dimensional feature space, when the class number increases, the area of each class will become tighter than before. Specifically, as shown in this figure, when training with only 4 classes, the region of each category is quarter, but if training with 8 classes, the region becomes more compact. Inspired by such observation, we propose virtual somax. Virtual somax is a classifier that serves as the training phase and seeks for discriminative features. In terms of formulation, it is achieved by injecting a dynamic negative virtual class term into the denominator of the original somax, and this virtual class is built at the same place as the current training feature xi. For its training samples, a corresponding virtual class is constructed. As the training going, this virtual class becomes dynamic and will continuously push the sample xi towards the corresponding class support vector wi, and the final optimization goal is to make state yi to be 0. Well, compared with our virtual somax, the conventional somax classifier learns towards a weaker goal. It stops working if state yi is less than a certain value. Moreover, we also provide some other understandings of the virtual somax. Interpretation from coupling decay. After rewriting equation 1 into equation 2 and performing the first-order Taylor expansion, a term of magnitudes of w and x shows up. Thus, minimizing equation 2 is to minimize the magnitude term, which can be viewed as data-dependent weight decay or weight-dependent data decay. Interpretation from feature update. For a linear layer, the feature update by somax and virtual somax can be illustrated by the blue and red arrows respectively. Obviously, the feature updated by our virtual somax is more closer to the class support vector wi. Experiments show that our virtual somax has similar convergence but higher accuracy on CIFAR 100 datasets. The visualization of the learned features shows that our virtual somax will force the features to be more discriminative than the conventional somax. And the similarity confusion matrix shows that our somax will force indeedly smaller intraclass variations and large interclass distances. We also conduct experiments on the small-scale object classification datasets like MINIS, CIFAR, and on the large-scale datasets like ImageNet, LFW. Thanks.
All right, this concludes the session. Have fun at the rest of the conference.